Hi, everyone. Welcome to the Q&A after the first session of this second day of Networking at Scale Fall Edition. I'm Neil Spring. I'm a research scientist in network analytics at Meta, and I like to explore and measure networks all the time, so I'm very excited to be moderating this Q&A session. Remember, there's apparently a little chat box in your Zoom window for submitting questions to our panelists. Unfortunately, as you can see, Christoph was not able to make it, but I have with me today Yimeng, who presented the millisampler burst analysis, and Brandon and Sharad, who presented network SLOs. So I thought I would just jump right in and start with Yimeng. You mentioned that you did this analysis of bursts and contention with millisampler data. What did you learn? What are the characteristics of these microbursts, and what implications does that give on how to further optimize the data center network?
Yeah, I think that's a good question. Our analysis result shed important insights that can guide the design of the buffer sharing, the congestion control, and also like the service placement algorithm. For example, we do observe that the bursts in our data center network is short and frequent. And if we look deeper into the burst characteristics, we observe that the contented bursts see more loss, though it can stabilize later when the burst lengths get larger because the congestion control can start to kick in. The higher variability in the buffer sharing make it hard for the congestion control to react before the queue overflow. So the result motivate the need for the joint exploration into the interaction between the buffer usage and also the congestion control algorithm. So it also calls for the new buffer sharing algorithm to reduce the buffer variability especially at the low contention level, for us to have a better network performance. Yeah, there are also some other interesting results, like we see large variance in the contention level itself. We see the differences in the contention level in different racks in different regions, or even within the same rack. Within like 1 second or 2 seconds, we still see large variance in the contention level. So those significant difference in the contention indicate that we could tune the buffer parameter according to the racks, according to the workloads, and also to handle the dynamics in a short scale, we may need to modify the buffer parameter dynamically to have a better performance.
Yeah, that's really interesting how you have to think about these changes that apply across all the different racks and across different points in time in order to get a really nicely functioning network. Just to spread things around, I want to ask my next question to Brandon. This is one from the audience. Do you convert the app to use these sized synthetic blocks for data transfer, or is that instead extracted from just the regular app and its transfer information? Did you have to modify that client application to get this data, or can you get it just from the server side?
Yeah, so the nice thing about doing this at the transport layer is that the application is completely unaware that we're doing these measurements, and it doesn't need to be modified in any manner. We are limited in some ways by the application's workload. So if an application is only sending 1 kilobyte of data and then stops, the network becomes completely idle, and then sends another kilobyte of data, we can't measure 50 kilobyte synthetic blocks because there's not 50 kilobytes of contiguous data being written to the network. But beyond that, if the application, let's say, sends 74 kilobytes of data, it's just writing out an object like that. And to be clear, this can be at the client or at the server. So it's writing that amount of data into the transport. Then we can take that information, and at the transport layer, we get told the application's doing these writes. We chunk it up into the different sizes, and we get the callbacks and the notifications about when that information or when those bytes were delivered by the network. So it doesn't require any application layer changes, and that's one of the reasons why we're able to use it so pervasively inside of Meta, because it's in all of our applications, and we can use it even inside the data center as a result.
Great. Sharad, do you have SLOs for different products or for different classes of products? Like, how does it depend on what the traffic pattern of the product happens to be?
Right. So yeah. So for the past couple of years, we have derived SLOs for a wide range of products inside Meta. So these range from products which don't have real-time requirements, like image downloads and video playback and feed loads, versus the ones that do, real-time audio video calling. The SLO derivation methodology remains consistent across these. What changes are the quality of service metrics, so the exact metrics that we use to measure the network conditions, which, as one might imagine, will differ, at least broadly speaking, between real and versus non-real-time products.
All right, rotating back up to Yimeng. Do you have a sense of how computationally expensive there is? How much server load is caused by the network monitoring at this timescale? This is another question from the audience. Is it worth it to pay the cost of this additional CPU use?
Yeah. So keeping the millisampler monitoring tool lightweight is the design principle that we try to keep through the process. So because we use the eBPF, which allowed us to inject customized code into the kernel. So and we do make sure that it's pretty CPU efficient and have minimal impact on the packet processing rate. So even in a line rate, so with the full capacity, the impact on the latency is in like the milliseconds or even microsecond scale, so which is pretty lightweight. And also we try to keep the memory footprint low. We use the sketch to estimate the number of connections, so we don't need to like keep information about the flow, so it doesn't use a lot of memory. And also the millisampler is not like continuously run. It will wake up every few minutes and then gets the data for a few seconds and then goes to sleep. So so in essence, we don't need to store a large amount of data on the server.
Awesome. So Brandon, there are a bunch of different ways of understanding network conditions. And I think between your talk and Christoph's, who's not here, there are, a couple of different approaches that we've seen just today. I was wondering if you could talk about how these two things differ, how we might think about contrasting them or using them together, or how they might complement each other.
Sure, yeah, that's a great question. And I didn't get to see Christoph's talk, unfortunately, because we were preparing for this session right after it, but I'm familiar with it from other conversations I've had. So I think the two works in this case have different goals. The responsiveness under working conditions is trying to understand challenges around buffer bloat. So if I create the worst case buffer bloat scenario, how does responsiveness change? And that's definitely important in terms of motivating improvements to buffer bloat or helping people understand why we don't necessarily want these large queues in the network, how we can optimize them through AQM. I think the work we're doing with network SLOs and the way we characterize the network there is saying, given how the network is behaving right now in the presence of our traffic, given our congestion control algorithms, how they're configured, and generally speaking, we use BBR, so we try to avoid buffer bloat and those types of problems. How is the network able to deliver these bytes to the remote? So I think they are trying to accomplish two different things. And I think, generally speaking, this is why when you're trying to characterize a network, there is no one solution that fits all use cases, right? You really have to think about what's your goal. Saying my goal is to characterize the network, that's not sufficient. You have to say, trying to characterize the network to understand, can my application behave well? Or in the other talk, we're trying to characterize the network to understand, is there potential for buffer bloat, and should we perhaps be employing AQM or other strategies?
Great, Sharad. How does the SLO change? So you solve this problem now, but if you did the same project 5 years ago, I think you would probably come up with a different answer. And maybe 5 years from now, you might end up with a different answer again then as technology evolves. Will the SLOs change? And how do you see this changing over time?
Right, that's a great question. So as the motivation for the network SLOs goes, we are trying to understand what are the network requirements or what the network needs to support for our apps currently in production, right? So as the apps themselves might evolve or how they interact with the network may evolve, this dynamic can change what the network requirements need to be to support the application quality of experience. So there is a varying dynamic here. The process what we have in place over here though is that just like to derive the thresholds, we also continuously monitor whether what is the predictive power of the network SLOs in terms of predicting the required application quality of experience. So if you observe, for example, that the network conditions themselves are not changing, but there's a divergence between the ability of the SLOs to predict what the application QoE is going to be. That's an indication that something has changed in how the application is using the network, and while monitoring this over long term, that brings up the case, or that basically builds a case for rederiving the SLOs at this point. So that's how we look at the transition of SLO thresholds over a period of time, and also the monitoring of networks, how compliant they are to these thresholds over time. So.
Great. Circling back to Yimeng, there are a couple more audience questions that I do want to pose to you. So first, there are, Meta runs a certain set of congestion control algorithms. There are other congestion control algorithms out there that try to use delay. Can you, I'm trying to rephrase it slightly, how would Millisampler help you understand the changes that those congestion control algorithms would be applying? Like, how will contention and buffer sharing change in the context of a delay-based congestion control algorithm?
So I think Millisampler can be very useful to help us to understand the dynamics of the traffic and then how the congestion control react to that. So for example, if we only have the minute level monitoring ability, then we would not be able to how the traffic react to the congestion algorithm. And also though, like the example I gave before, talk about like the job in the buffer sharing. So actually the variation in a buffer share availability would also affect the performance of the congestion control that based on the delay. Because if like it has large buffer, but then it has large variance, then it takes time for the congestion control to kick in. And also we do observe that the variation over the RTT time scale, so that could also affect the performance of the congestion control algorithm.
So coming back to the network SLO work, Brandon, you talked about quality of experience, but I'm curious if you think it's reasonable to apply the same approach to understand service health, not something that is so much user facing, but for services in a data center, they might also be sensitive to network conditions, but they have different approaches, not using quality of experience, but instead using some performance indicators that the service happens to have. How would you apply your approach there?
Yeah, so that's a great question. And again, one of the reasons that we've done the network characterization, or one of the advantages, so to speak, of doing the network characterization as a transport layer is we can reuse the same approach on any application, and that means it's also applicable to applications or services running in our data center. And so we use the same thing there. In terms of in our data center, there's more TCP traffic. So that means that we have a version of synthetic blocks that's specific to TCP, has slightly reduced sensitivity in terms of what it's able to measure for network conditions, just because of the limitations of Linux kernel timestamps for socket timestamps. But beyond that, we use the same approach for characterizing the network, and we can use the same approach as well for understanding the relationship between the network conditions and any key performance indicator that an application has. So the same approach that Sharad described earlier, we could say, well, we expect this application to be handling X queries per second or some workload, and we can say, not only how is it related to network conditions, but we can also understand in cases where it's not due to the network conditions, right? So we can use this to diagnose cases where an application's KPI may be degraded and it has absolutely nothing to do with the network. So it's a very powerful tool, even though we've discussed using it for the end user right now. In this talk, it can be applied in many other ways.
Okay, so a question for Sharad. One of the things that I've experienced in trying to understand network measurements is that, the first 80% of the measurements that I look at are like, teach me something about what's happening in the actual network and not necessarily what I was looking for in the first place. So I guess I'm curious, when watching the talk, I'm curious what you see. Like, do you see events? Do you see weird things like everybody in the stadium? Do you see effects of New Year's Eve or something? And was there anything that surprised you when you started digging into this data?
Right, absolutely. So in the last couple of years of looking at how SLO compliance look at networks across the world, one thing that we have observed is that compliance is actually very sensitive to traffic conditions between Meta's edge and the end users. So organic events like festivals, New Year's Eves, sports events, they actually show up fairly nicely in terms of how the compliance changes during those times and for those specific parts of the network. So we've actually used them as a fairly predictive signal as to whether the edge user network has the capacity to support certain levels of application requirements. As I mentioned, they've also shown up in ways to shed light on when Meta's edge network had sufficient capacity to handle these traffic loads, and if it didn't, and was it sending traffic to parts of the edge network where the parts were no longer compliant, and this has sparked conversations about how to prioritize edge capacity investments in part of Meta's network. And finally, I think one of the things that was slightly surprising for me was that we obviously expected that a large part of SLO compliance over long periods would be dominated by access technologies, and where there are slower wireless networks, for example, you would see lower compliance and so forth. But sometimes the SLO data also reveals interesting patterns of traffic engineering that happens inside ISP networks, where the access technology may be expected to support a certain application requirements, but depending on users' data plans or ISP policies, it doesn't show up as that. And that's just an interesting insight to parts of the network where we traditionally would not have from our vantage point in the internet.
That's awesome. I think we have time for one more question, so I'm going to give the last one to Yimeng. For this, also from the audience, from this millisampler work, identifying, I think this goes back to the beginning slides of the talk, identifying and alerting to programmers about accidental application synchronization seems important and hard. Have you thought about automating this sort of detection to get that information back to programmers who shipped the sort of subtle bug about that led to accidental synchronization and large bursts that are synchronized?
Yeah, that's a good question. So we have the automated analysis on the synchronized bursts, and we are actually monitoring the services that generate a lot of synchronized bursts and cause contention in the rack level. But then in terms of whether it is caused by the application, I think now we don't have like a very good mechanism to distinguish whether it's this application behavior or it's because of the service placement algorithm. I think what is more important for us is once we're monitoring that the contention increase to an alerting level, and then it starts to have starts to cause performance degradation for the services, and then we could work with the service owner to start to investigate what actually causes the problem and then find a mitigation there.
Brilliant. So unfortunately, that's all the time we have. I hope everyone enjoyed that as much as I did. I would like to thank our speakers, Yimeng, Brandon, Sharad, and Christoph, who couldn't be here, for sharing these rich problems in understanding the network. And to all of you for watching. Your participation encourages us to continue to share. Next, I'll pass this along to Tanuja to introduce the last session of our Networking at Scale event.